Okay, hello everybody. Today we are going on to our second day in this unit for sequences and series. Today's official title is called Infinite Series. We're talking about infinite series, and we're going to more specifically talk about like geometric infinite series. So we understand what geometric sequences are. We're going to continue with that idea, look at different types of geometric series and what a series is as compared to a sequence. And it's going to lead us into more lessons with dealing with infinite series. Okay? So let's start off with a little bit of a warm-up, practicing what we did yesterday with sequences and converging and diverging. Okay? Remember, sequences is a list of numbers, okay, that follows some pattern, and the pattern is given by A sub n, A sub n, A sub n. Now, what we learned about yesterday, converging and diverging, I want us to really understand what those two words mean. Converging means that the list of numbers are approaching a specific value. So how we talk about this is by discussing the limit as n is approaching infinity, as we approach that infinite term of our function. Okay? So we're curious about what happens as this approaches infinity. Okay. Well, there's a cool way that we can rewrite this specific problem. We can, since they both have a power of n, you can actually write this as the limit as n approaches infinity of e over 4 raised to the power of n, right? We're just undistributing the power. Okay. Now, we're going to learn something later on with geometric series, but it's all about if we have a number right here raised to the power of n, this is almost like an r value, right? This is our rate, our ratio. It's in the form of a geometric sequence. The power is just not n minus 1, but that's okay. And it turns out that if r, which in this case is equal to e over 4, it turns out that the absolute value of r, which is the absolute value of e over 4, if it's less than 1, okay, which in this case e is 2 point something, so this is less than 1, it converges. Now that's an idea you've learned in the past with geometric sequences and series, but basically the idea is that if the rate is a fraction, your numbers are getting fractionally smaller and they're approaching 0. Like if the rate was 1/2, 1/2, 1/4, 1/8, 1/16, it's getting fractionally smaller to 0. That's kind of the idea there. Let's look at this next one. This next one is a sub n equals the natural log of e squared to the n over 5n. Boy, oh boy, is that a big boy and girl problem. I mean, the only thing we can really do to simplify this is maybe distribute the n to 2. Let's look at this. So this is kind of an interesting idea here. Okay, you're going to like this. Remember the power rule for natural log? What happens if we have a power in the quantity for ln? The power rule says it can come down front. So really this is 2n times the ln of e over 5n. Okay? And ln of e just crosses out. ln of e is 1. So what happens if I discuss the limit as n approaches infinity of 2n over 5n? Well, the n's cancel, or you can think about that as having the same power on top and bottom. But basically, the leading coefficient is the limit. It's going to equal 2/5. So this does converge. It converges to 2/5. Okay? This next one is not so much geometric or following the principles of just some simplification, but I think this is an interesting topic. -1 to the n, that's alternating. So we know that means alternating. But really what's interesting is so technically if you think of this as the limit as n approaches infinity of -1 to the n, and think of this as like 3 over n to the 1/2 power. Now there's 0 n's on top. So think about us having a higher degree on the denominator. And if we compare the powers together, that means that it's going to be 0 as it approaches infinity. So what we're used to seeing with 0 approaches infinity is something looking like this, like a function doing this. But because we have that -1 here, it's actually alternating and getting closer and closer and closer to 0. It's actually a really cool concept. It's going negative, positive, but it's getting fractionally smaller to 0. So this one does converge as well. So really, the justification we're using for convergence right now is some geometric rules or some rational end behavior rules, but that's about it. Okay. All right. So my goal for this video is to do just a few slides introducing the topic, so we're not completely, wasting our time, not wasting, but exaggerating our time in class. Okay. All right, so we're talking about series today versus the difference of sequences. One thing that I'm going to clarify is a lot of what we're talking about and what we're going to be seeing these next few days are going to be power series. Okay, that's in the form of a power. So like the form you're going to see the patterns in is like x to the n. So that's like a geometric series. So honestly, power series and geometric series can sometimes be written interchangeably. The names can be classified interchangeably. We're going to see differences in the types of geometric series that classify it as a power series, more so later on throughout the lessons. But for now, I want us to understand what an infinite series means. Okay? So series as opposed to sequences means the sum of an infinite sequence. So it's not just going to be a list of numbers, but adding up the numbers. So like a sequence is in the form A1, A2, A3, it's a list of numbers, right? Now the summation, which I'm going to use, I'm going to write it this way. The summation, okay, the sum of the infinite sequence, and we've seen a summation before dealing with the definition of integrals, would be like taking the sum of the first term to the infinite term of my list of numbers. So what this looks like is my first term, and instead of a comma, we're going to put a plus there, plus my second term, plus my third term, plus ... all the way to my nth term, and even further to my nth plus 1 term. I mean, we can keep going to infinity, but the sum, all right, a series is the sum of those. Okay? And more specifically, if I say S sub n, instead of taking the infinite sum, we would take the sum from n equals, or I'm going to use k here because I'm about to use n for something else. We would take k equals 1, meaning the first term, to our nth term. So not the infinite amount of sums, but just a partial sum of we'll use k since that's the one letter I used here. Basically what this is doing a sub 1 plus a sub 2 plus a sub 3 plus ... all the way to my nth term. Now that could be the sum of the first 10 terms, the sum of the first 12 terms, the sum of the first 100 terms. But it's different than taking the infinite sum like I was doing above here. Okay? So again, what I just said is that's called a partial sum. Okay? Partial sum. So that's in the form S sub n. It means we take the summation from k equals 1 to some discrete final point of my list of numbers. Okay? So this notation right here means partial sum. Okay? This n right here means to take the sum to this term. Okay, I want to really specify that. All right? So for instance, if I were to say S sub 1, that means take the sum of the first term, right? That would be k equals 1 summation to 1 of a sub k, which literally would just be a sub 1. Like if I were to say S sub 2, that would mean take the sum of the first term to the second term. So that would be like, for instance, a sub 1 plus a sub 2. Or if I were to say the sum of the first three terms, so 1 to 3, that's going to add up from my pattern, the first term plus the second term plus the third term, and so on. Okay. Okay. Now, here is a thought that we really need to make known and understood. And I know this is going to sound confusing, and I'm really going to try my best to, especially in person, explain the difference. Okay. If the sequence of the partial sums, okay, has a limit value as n approaches infinity, if it equals something, okay, we say the series converges to the sum s. So what I mean, when I say the sequence of partial sums, I mean S1, comma, S2, comma, S3. So like what I figured out here, here's S1, here's S2, here's S3. If those sums, if those partial sums are approaching a limit value, we say the series converges to that sum. Otherwise, the series itself would diverge. Okay? So let me try to explain this graphically, first of all. Let's say, here's S sub n. We'll say this is S sub 1, S sub 2, S sub 3. Now, this is different than talking about the convergence and the divergence of a list of numbers. Like if I'm talking about A1, A2, A3, if I'm talking about these approaching a number, I mean that the list of numbers itself is approaching a specific number. But if I'm talking about that versus S1, S2, S3, I'm talking about the sums, the partial sums approaching a specific number. And if I talk about the infinite amount of partial, like if I talk about the infinite amount of partial sums, that would eventually be the infinite sum. But let's say like we have a number right here, it's 5. Let's say the first partial sum is 20. Let's say the sum of the first two terms is 18. Let's say the sum of the first three terms is it goes all the way down to 6. Let's say that as I keep taking more and more sums, they eventually approach 5. Then the sum of the infinite amount of terms is 5. Converge to a sum of 5. And we're going to see this algebraically and graphically a lot later on. But what you're used to probably seeing with an infinite amount of sums, S1, S2, S3, is you're used to seeing like, okay, the sum of the first term is like 5. The sum of the first two terms adds up to 10. You're used to sums adding up to a greater value as you go to infinity. Let's say the sum of the first three terms is 20. That would be a divergent sum. Like you won't be able to compute the infinite sum. Okay? That would be like an arithmetic series in situations like that. Okay? So again, I will try to graphically show the difference between a sequence of numbers versus a sequence of partial sums converging and diverging. There is a difference, and I want us to be able to see that difference. And I think this next example does a pretty good job of it. So I think what I'm going to do is I'm going to end with this next slide, okay, and then we'll pick up from this one, okay? It says, does this converge? Okay, this is a series because we are adding a bunch of numbers together. Okay, here's what I mean. First of all, the list of numbers is 1, -1, +1, -1, +1, -1. It just goes on that way forever. Okay, the series, okay, the infinite series, we'll say, is me doing 1 plus -1 plus +1 plus -1 plus +1 and so forth. So what I want us to talk about is it's asking about the sum itself. So we're talking about an infinite series. It's talking about the sum of it. I want us to use this as an example to discuss the difference between the list of numbers converging and diverging versus the partial sums converging and diverging. So for instance, okay, let's do, we'll call this A sub n and this S sub n. So the list of numbers itself, the sequence or the list of numbers itself is going 1, negative 1, 1, negative 1. It looks like this. It's going, the first term is 1, the second term is negative 1. The third term is 1, fourth term is negative 1. It's alternating between 1 and negative 1 infinitely. So the list of numbers doesn't converge. It just keeps oscillating between 1 and negative 1. Let's talk about the infinite sum or the partial sum. So like let's talk about S1, S2, S3. S1 is just the first term. S2 is me doing 1 plus negative 1. S3 is me doing 1 plus negative 1 plus 1. S4 is me doing 1 plus negative 1 plus 1 plus negative 1, and so forth. So if I were to plot those partial sums, S1 is 1, S2 is 1 plus negative 1 is 0, S3 is 1 plus negative 1 plus 1, which is just 1, S4 is 1 plus negative 1 plus 1 plus negative 1, which actually goes to 0. In fact, the infinite sum oscillates between 1 and 0. So there's a difference between a list of partial sums and a list of numbers. I need us to understand the difference of that. Okay. So we're going to keep that in mind. There's a couple things I want to talk about with this slide. I'm at 17 minutes, and I think I'm just going to end with example 1, and I'll pick up with example 2 tomorrow. But what I want us to understand is that the general term here for this series, I want us to know what A sub n is. Okay. So first of all, what's going on between each of these numbers is we're simply just multiplying by negative 1. We're multiplying by negative 1. That makes this a geometric sequence of numbers. So the explicit formula here is just A sub n equals A sub 1 times r to the n minus 1. We learned that in our last lesson. So in this case, my first term is 1. My rate is that I'm multiplying by negative 1. It's being raised to the n minus 1 power. Okay. So if that is the explicit formula, then the summation, my partial sum, is going to be the summation of k equals 1 to n of 1 times negative 1 to the k minus 1 power. Okay. And if I'm talking about my infinite sum, then n would just be infinity. Okay. So this is the representation of my partial sums. This is the representation of my explicit formula. Okay. Now, I'm going to stop right there for now. We're going to pick right back up with this in our lesson. I got to 18 minutes, but this gives us a good buffer zone for me to keep going when we get together in class. Okay? So good job. We'll pick up with example 2 tomorrow, and hopefully as we do more examples, this will make more sense. So, good job, everybody. We got a good intro into partial sums, infinite series, that kind of deal. All right.